Okay, YouTube, in this video we're going to continue to look at function notation and specifically a type of equation that we like to solve quite a bit of the time with function notation, which is this equation right here. Go and solve this. And so what you're going to see here is essentially this. If I had two functions, f of x and g of x, then perhaps what we want to do is we want to find all inputs for which these two functions have the same y values, okay? So we're looking for a particular x value that our two functions have the same y value. Then what we do is we kind of present a peculiar situation, whereas if I had, say, one function, f of x, maybe, and another function here, let's call this one g of x. Maybe g of x looks like this here, g of x. What we want to do is go find all the x values where we have the same y value on that graph. So right now what I can tell you is I can spot a couple of these, but these would be these right here. We would say that the f of x value and the g of x value are the same right here, and the f of x and g of x, or the y value for both graphs, are the same right here. And so that's the case, then what we're really looking for here are these, say in this particular case here, these x values right here. And so when we go and look for the solutions to f of x equals g of x, which I noticed this should be f of x equals g of x, then what we're doing is we're solving really for all the x values of the graph which our graphs intersect, at which our graphs intersect. So we would say that we want to, let's go ahead and type this out here. We want to solve for all values of x at which our functions have the same y value or function value. So graphically speaking, these are the input values at which our graphs intersect. And so that's a pretty neat thing we want to find a lot of the time. And so let's go ahead and talk about how we can do that here, kind of like in our last video where we said we wanted to solve the equation f of x equals 0, and so we just plugged in 0 for f of x. What we're going to be doing in this video is we're going to be setting f of x and g of x equal to one another and then solving for that value of x. So in order to do this, solving this, we're going to set f of x equal to g of x, and then we're going to set equal to 0 on one side, and then we're going to solve. And I'm going to write a note here, often by factoring. It's an important thing for us to be able to do. So solve by factoring. So let's take a look at letter A here. What we have are two functions, f of x and g of x, and it looks like they're both second degree polynomials here. Not that that's that important yet, but a couple of parabolas. And so what we want to do is we want to find for letter A here, what are all of the x values for which f of x equals g of x. And so what we do is, again, like in our last video here, we're going to make substitutions. So substitutions, what I mean by this is we're going to take f of x out and g of x out. We're going to plug in their rules. So since I know f of x is x squared plus 1, and because I know g of x is 3x minus x squared, then what we end up with is this really expression right here, which means the same thing as what we started with. So like I mentioned here in our directives, we're going to set one side equal to 0, and I feel like it would be easiest, okay, to go ahead and add this x squared and subtract 3x off of the right. And we'll do the same thing over here. We'll add an x squared and we'll subtract 3x. So what happens is we systematically eliminated every term on the right side, and on the left side we have x squared, and x squared is a 2x squared. This negative 3x here, this negative 3x had no other x's to go with, and this positive 1 was a constant, had no other constants to go with. So since we've got the set equal to 0 now, again, what we want to do is we want to solve this by factoring. And so if it's factorable, I notice that this is a trinomial where a value is not 1. A doesn't equal 1. And so in this case, I cannot simply just think of two numbers that multiply out to be 1 and add up to be a negative 3. We're going to have to play around with this a little bit. So because in FOIL, right, FOIL, when we do FOIL, these first two terms here are always responsible for giving us this term here. That's our f produced term. And because when we multiply our last two terms together, that's always responsible for giving us our last term here, then this is like our L term, which means that when we do our outer and our inner and combine like terms when we FOIL, okay, we produce the middle term there when we combine like terms. So essentially what I want to do is this. To unfoil this, we're going to start with our f and our L and do those first. That is to say, I want to find out what two things could I multiply here and here that give me a 2x squared. And the only two I can think of are a 2x and an x. So with respect to the FOIL here, unfoiling, we've got the F. Now let's do the L. And I would think of two numbers that multiply out to be a positive 1. Now keeping in mind that this is a positive, that means that what I put here and here have to have the same sign. But I noticed that this has to sum to a negative in the middle. So I'm going to make these both a negative 1 here. Now here's the kicker. I'm not sure if this actually works or not until we actually test it. But the cool part about this is the only thing that we need to test are the O and the I. We're going to multiply the outer and inner terms. So I take 2x times a negative 1 and I get a negative 2x. And I'll take a negative 1 times x and I get a negative x. If I can multiply the outer and inner and add them up and I get this middle term here, which we do, so that's cool, then we've factored it properly. And if I didn't, then what I might try is just go ahead and switch the negative 1 and negative 1 around if there were any more variety. So since now that I have this set to equal to 0 and factored, what we're going to do is we're going to go ahead and set each of these factors individually equal to 0. So we get 2x minus 1, either that was 0 or x minus 1 had to be 0, but somebody here was 0. So if x minus 1 is 0, we certainly get that x is equal to 1. And if 2x minus 1 is equal to 0, we would have to add 1 to both sides, so we get 1 here. But this would lead to the fact that we get x is equal to a half. So just to show you this here, I want to pull open Desmos. What I've done was I put in f of x and g of x. And you can see these couple of parabolas here. But what I want to look at are what are the x values for which our graphs are exactly equal. So let me highlight this here. These are the 2 points of intersection, but what we were looking for were these x values at which we had the same y values. And so we were able to solve for a half, and we were able to solve for 1 as the two solution values for which f of x equals g of x. So let's go ahead and try this again here, and a little bit different in the factoring situation, or factoring department this time, a little bit more variety. Again, what we want to do is we want to solve this equation right here. So let's go ahead and make our substitutions with our function output expressions, but we'd say f of x is x squared minus 1 here, and our g of x is negative x squared plus x plus 2. So negative x squared plus x plus 2. And so now that we've got these set equal to each other, I want to go ahead and set one of these sides equal to 0. Now it'd be really easy to clear the left side that only has 2 terms, but because our leading term here, our leading coefficient is negative, I'd kind of like that to be positive. So I notice that if I add x squared and subtract x and subtract 2 from both sides, so we add an x squared, add x squared, subtract x minus 2. What we're going to do is wipe out all these terms on the right, and what we end up with on the left is 2x squared, only negative 1 of these x's, and in terms of constants, negative 1 and negative 2 is negative 3. So now we get a situation where, again, we want to unfoil this. So let's do what we did last time. Guess and check wise, we always start with the f and the L. So what can I put here and here that give us 2x squared? So again, 2x and x, those are really our only options. And then what can I put in the last part of these to give me a negative 3? So now here's where this is a little bit different. Negative 3 could be 3 and negative 1, or negative 3 times a positive 1. Or you can switch their order. So what I'm going to do here is I'm just going to put a negative 3 and a positive 1. And what I'm going to tell you is we've at least gotten the f and the L part right. We're going to get this term and this term. The question is, do we get a negative 1x when we multiply the outer and the inner? So let's go ahead and multiply these. We get 2x times 1 is 2x, and negative 3 times x is negative 3x. The interesting thing here is that I have actually stumbled across what we needed in the first place. So these are the appropriate factors here. Great. Now let's assume I had put a minus 1 plus 3 to begin with. We wouldn't have gotten this middle term. So if that ever happens, what you do is you just switch, say, the 3 and the 1 around and try to guess and check till you get it to work. But now because I have both of my factors here multiply out to be 0, then either 2x minus 3 equals 0 or x plus 1 equals 0. So this one over here, a little bit easier to solve. We're going to get a negative 1 for our x value. And solving this, we would add 3 to the right side here and divide by 2. We get 3 halves, or 1.5. But what I again want to go see is this. If I were to graph both of these functions here, both of these parabolas, what you're going to see is these 2 points of intersection. The x values are 1.5 here and negative 1. So let's take a look at what we got here. We got 1.5 and negative 1. Cheers.